I'll be talking through the solution to question 4 from the 2015 examination paper for numerical methods for partial differential equations. So question 4 gives you the 1D advection diffusion equation written using differential operator notations. So this means this small delta, little delta subscript t in front of the u means the derivative of u with respect to t. So likewise, small delta x in front of the u means the derivative of u with respect to x. Okay. In question 4 part A says define t, x, v and alpha and give a physical interpretation of this PDE when alpha is equal to 0. Well, t is time as usual for partial differential equation. X is distance. Okay, that's your spatial distance along the domain. V is velocity, and alpha is a diffusivity parameter. Okay. So when alpha is equal to 0, this right hand side here is equal to 0, and we have the advection equation, which is well known. Okay, part B, 4A, part B, part 1. Okay, write down expressions for the first order derivative of u with respect to t and the second order. Okay, so the first order one is easy. We just rearrange this by subtracting v delta x u from both sides. Okay, so that gives us our first order derivative. The second order, we simply differentiate this term with respect to t. So if we do that, okay, the key thing here is it doesn't matter what order our derivatives are in. So here we've got delta t, here we've got delta x. Well, if I switch those order, or that order, and I've also expanded out the bracket. Okay, so we have minus v delta x multiplied by delta tu, and we have alpha times the second order derivative multiplied by the first order derivative again. So these two expressions here and here in brackets, we simply substitute that in again. Okay, so we substitute it in again, do some expansion and rearranging, and we end up with this expression here. B part 2. Okay, so here we've got the unsplit differential Marching operator for the advection diffusion equation. Okay, so here we have it. And this LAD essentially this is an operator which is applied to u in order to give us the solution at the next time step. Okay, so that there, what we do is we substitute in all of that, and that's an operator which is applied to the current time step in order to give us a solution at the next time step. Okay, so all you do is you take this Taylor series, so going forward by one time step. So we've got u plus delta t times the first order derivative of u plus delta t squared over 2 times the second order derivative. Okay, and all we do is we substitute in our first order derivative and second order derivative. Okay. So once we do all that, we rearrange and we factorize out u. So this term in the square brackets is my LAD, and you can see it's equal to what we had to show. Okay. Part C says derive the second order differential Marching operators for the separate advection and diffusion equations, and show that the split scheme. So this is where you solve the diffusion equation before solving the advection equation is the same as the unsplit scheme. Okay, so we take the advection equation, this is when alpha is equal to 0, and again if we derive the first derivative and the second derivative using the same method up here. Okay, so we've done it there, substituted into the Taylor series as before, rearrange, and you get this is your advection operator. Oops. Excuse me, I'll just make that bigger again. Don't know what's happened there. Oh. Okay. Doing similar for the diffusion equation. Okay. We have the first order derivative and the second order derivative, and again substitute it into the Taylor series, and we have the diffusion operator. Ignore that A. That should be a D. Okay. Now to combine them, all we do is essentially multiply them together. So we multiply this by this. Okay. And a key thing to notice here is our error term is big O delta t cubed. Okay, so any error term which is bigger delta t cubed or more will be ignored because that's already taken into account by that error term there. Okay, so multiply them together. Okay, do the cancelling out, and you get down to this line here, which is, scroll up, which is what we were trying to prove. So we proved that the split scheme, okay, we've applied the diffusion and the advection, is the same as the unsplit scheme. Okay, why would we want to do this? A couple of reasons. Split schemes have better stability properties. It allows us for different time steps to be used for each equation. So we could use a different time step for the diffusion equation as for the advection equation. And give another example how split schemes are used. Well, in multi-dimensional PDEs, we can split the problem into 1D PDEs. And so we can split the problem up, solve using simple 1D schemes, and combine them to give us a 2D solution.